this video, we're going to continue talking about average value. Specifically, we're going to be talking about something called the mean value theorem for integrals. This result is going to show us that anytime we have a continuous function like we did in our previous example, we will be able to find some point where the value at that point is actually equal to the average value. So let's see how we can go about finding this mean value theorem for integrals. First, we want to just remind ourselves what the mean value theorem that we learned back in Calc 1 actually says. So let's recall that the mean value theorem, which I'm going to call MVT, says that if we have a continuous function, let's call that function g, if g is continuous on an interval ab and differentiable on the open interval, then there's a point in that interval where the derivative at that point is equal to the slope of the secant line over the interval. So we say then there is a c in this interval where g prime of c equals, g of b minus g of a all over b minus a. So the big idea of the mean value theorem from Calc 1 was that in an interval there will be a point where the slope of the tangent line to that point, in this case c, will be equal to the slope of the secant line over the interval. Or in other words, there'll be a point where the instantaneous rate of change was equal to the average rate of change. So that's what we know about the mean value theorem for a function. But let's say that g is actually a function that's equal to some integral of f. So let g of x be equal to an integral from a to x of f of t dt, where our function f is continuous. And then we want to take this mean value theorem and apply it to this specific function g to see what we can say for this mean value theorem for integrals. So if f is a continuous function, then g, this g equal to this integral, is also continuous and differentiable. And that's a fact that we learned back with the fundamental theorem of calculus. So then our function g is continuous on our interval ab and differentiable on the open interval ab. Okay, so we can apply this mean value theorem here to this function g. So what are we going to be able to say when we do that? Well, now we can say that, let's do another color. So after applying MVT, we can say we have a c in this interval AB where g prime of c equals g of b minus g of a over b minus a. Okay, that's exactly what the mean value theorem says for g, but what about trying to convert this to being in terms of this function f, whose average value we might have been interested in taking? So notice that if I have g of x equal to this integral, that g prime of x, if I take the derivative of an integral, I undo that integral. So g prime of x would be equal to f of x. So this g prime of c is actually going to be equal to f of c. Okay, so I have this, but now g prime of c, is equal to f of c, and our g of b, well, I can replace x here in this definition for g of x with b. So my g of b is an integral from a to b of f of t dt, and my g of a is an integral from a to a. And then this is all over b minus a. So we would recognize we have this division by b minus a. That's something that we had in that average value formula. Well, what do we know about this integral from a to a, well, we know if we take an integral from some number to itself, that's just equal to 0. So this gives us that f of c is equal to this integral from a to b of f of t dt all over b minus a. And this is exactly the formula for average value. So we see we've said that we can find a point as long as we have a nice continuous function f, so that the value at that point is equal to the average value of the function. This is summarized below here in this statement for our mean value theorem for integrals. If f is continuous on AB, there's a point in that interval so that the value at that point is equal to the average value of the function, which we know is equal to our average value formula of 1 over b minus a times the integral from a to b of f of x dx. Okay, we can also rewrite this and get another geometric interpretation that the integral from a to b of f of x dx is then equal to f of c times b minus a, just by multiplying both sides here by b minus a. So what does this mean in a picture? Well, if I have my graph, let's say of my f of x on the interval from a to b, we know that the integral from a to b of f is the area under that curve. So that's the left-hand side here. And that's saying that that area is the same as the area of a rectangle with height f of c and width b minus a. So if we take this same graph here, a to b, I know I have this f of c, which is also equal to my average value. So I know if my average value maybe is along here. So if I took my rectangle piece here, oops, let me just use a different color. The area under this rectangle would be the same as the area under my whole curve. Okay, so you can think of what's happening here as, let me use just another color. What we're doing is essentially saying that this area here that would be cut off from our average value is equivalent to this little extra that comes from the rectangle. Okay, so we get that nice geometric interpretation as well of that area of that rectangle being the same as the area under the curve. So that's a nice result from our mean value theorem for integrals. Now let's look at an example where we can apply this theorem for a particular function. So we have the function f of x equals 1 over x on the interval from 1 to 3. And we want to do a couple things, including find the average value, find the point where the function is equal to that average value, and then look at the geometric relationship of the area under the graph of f and the rectangle whose area is the same as the area under that graph. So first we can just find the average value. So the average value of our function will be 1 over b minus a, so in this case 3 minus 1, times the integral from 1 to 3 of 1 over x dx. So we know that the antiderivative of 1 over x is log of the absolute value of x, and we're evaluating that from 1 to 3. So we have 1/2 times log 3 minus log 1. And then we know that log 1 is equal to 0, so we have 1/2 log 3, or log 3 all divided by 2 for the value of the average value for that function. Okay. So let's look at now finding a point where the function is actually equal to that average value. We know that we'll be able to find such a point because this function is continuous. So we'll set that average value equal to our function and solve. So if I have log 3 over 2 equals 1 over x, I know that means x has to be equal to 2 over log 3. Or in other words, our point C would be 2 over log 3. Okay, so let's see what this looks like for the geometric interpretation. So here I have my graph. This red line here is my graph y equals 1 over x. And this blue line here is the average value of the function over the interval from 1 to 3. So this is our f average. Okay. So geometrically, we know that the area under our red line here, the curve 1 over x from 1 to 3, so that would be this area, will be equal to the area under the average value line, whoops, from 1 to 3. Okay, whoops. So let's see, that'll be from here to here. Whoops. So it'll be all of this region here. Okay, so those have equivalent areas. We can also see what that means here. So that means that this little bit here essentially can be thought of as being chopped off from that piece and used to fill in the part here of the rectangle. Okay, so that gives us a nice geometric interpretation, as well as also seeing the point C here, where we're actually equal to our average value.